Hello there. In this video we're going to walk you through how to set up Nigiri in a new project, and we're going to do this as real time as possible. So first you need to create your new project. For this walkthrough I am going to use Unity 2019, so Nigiri should work with every 2019 and every editor release after this. If you encounter any breaking issues in more recent Unity versions, then let me know and I will endeavour to fix them post-haste. So first I am going to do this on my NVMe, not my RAID, so this happens as quickly as possible. There we go, walkthrough, 2019 selected. This always takes a minute, but I don't have the best internet in the world, and this depends on your internet speed to a certain degree. I'm performing this walkthrough on my little 16:9 monitor so that it's easier to see the video. Of course, if you have an ultra-wide or you can afford an ultra-wide, I highly recommend them for actual any serious work. Extra real estate really makes things much more straightforward for you. Okay, so we have our new project. So what we're going to do is set up our editor windows as we are accustomed. I will for now. Now, the first thing we want to do, we go to our project settings, is set the project to linear color space. Nigiri works in linear, and linear is required. So once you set that to linear, next up we will import Nigiri itself. So we go down to Assets, Import Custom Package, and now navigate to our package file. There we go. This will take about a minute. The system is made up of quite a few compute shaders, so it does take a minute to compile them all. Okay then, so our package is now imported. Now, if on importation you receive any red errors down here complaining about conflicts between DLLs or plugins, because some other assets already in your tree might also use these libraries to help them, such as system buffers, system memory, system runtime compiler services, and system threading tasks. If any of these have a mismatch or a clash, you can safely delete the ones in the Unity directory, restart your editor, and it will find the single version and then work adequately for you. So now that's imported, we need a scene to work with. So we'll just pick one. We use this for no reason other than it's a good test of the system because it contains about 10,000 prefabs, and it doesn't have the best results in Nigiri, but it does actually stress test it quite well because having to manage 10,000 objects in the back-end systems is yes, it's a good stress test. There we go. I will pause the video until this is finished. Okay then, so we now have a scene imported to work with. So we will open that up. Yeah. Bring ourselves outside of this wall here. There are a few steps at this stage. First, we go into the lighting controls to make sure the main directional light is set. And turn down the intensity of the ambient. Make sure both of these are unchecked. And then at that point, if we click generate, just to bake the reflection probes. It is worth saying at this point that Nigiri is designed to complement Unity's existing lights and reflection probes as opposed to completely replacing them. It's a complementary system basically, as you can't actually turn these things off in engine fully to begin with, so we may as well use them as opposed to fighting against them. There's also support for emissive objects as a free light source, as anything set emissive will emit light in a scene without the rendering overhead of a standard Unity light. So if you did want lots of lights in a scene without the large render overhead, then emissive subjects rather than Unity lights is a solution. You can replace one with the other. Looks like it's almost done. Just wait for that to finish. And before we do anything else, we'll also just bake the occlusion quickly. I'll just put that through with the defaults. There we go. Okay, now we are ready to perform our setup. The first thing to note is that because Nigiri is a hybrid lighting solution, hybrid baked and real-time, it has the functions for all static geometry in your scene for pre-calculating the voxel positions and then streaming them in at runtime to accelerate the initial build of the system. The most important point here is that meshes must be imported with the read-write flag enabled, though to make this easy, in the Nigiri menu under Tools, there is an option which will attempt to re-import all the meshes in the scene with this flag enabled to make it quick and easy for you. It may miss some, but about 99% of the time it will do everything you need. There you go, meshes processed, 12,000. At this point, we can perform scene setup. For this, there is another easy setup option in the menu, Tools Nigiri, Easy Scene Setup, which will perform several steps for you. Now, for reference, the steps of manual setup, I will link to a wiki page detailing in the description below. There we go. See, at this point, we now have a Nigiri manager object in the scene, which will show you exactly how much work it's working on. Anytime Nigiri is performing any background processing, this little icon will appear in the scene view window to let you know that it is performing background work. This background work it is performing right now is pre-baking the scene geometry for you. Every so often, while during the baking, it will batch out the generated information to the database, as you'll find if we go to your assets in streaming assets, and then Nigiri is where it stores all your voxel data it has generated in SQLite databases. As you can see here, it is using 80% of my 32 CPU threads. It is the distributed threaded nature of the architecture means that it is designed to scale to use as much CPU time as you have available in edit mode without actually outright starving you for resources by targeting about 75% of your CPU threads. In runtime mode, it is more constrained and calculates to using about 2 and 4/6 depending on how many cores the user has, so that plenty of CPU time is available for actual running game processes, audio, without actually starving the CPU out at all. But in edit mode, it just scales up to as much resources as you can handle it to ensure the work is done as expediently as possible for you as a developer. Now I'm going to pause this for a moment while it finishes baking the scene, because it takes about 5 minutes with about 10,000 prefabs to work through. There we go. It's almost finished. And we're done. So at that point we will save the scene. It will flush the last of the generated data to disk for us. There we go. Now I'll walk you through the steps this has actually performed for you. The first thing you'll see is it has added a prefab called Nigiri Manager. This is like the brain and central coordination of the distributed nature of the lighting system. Here we have the voxelization settings. The area size you'll see has been preset. Voxel size, and actually we'll make this a little bigger. Octree memory, bitmap and emissive. Now the area size is basically the area from the center of the scene, centered on the 000, that the global illumination will apply to. Voxel size is the size of the voxels, which are calculated to a specific size, so these both control the number of voxels in a scene. I believe medium sets the voxel size to 1 meter, small is half a meter, very small quarter of a meter, and then large and very large are basically 2 and 4 meter voxels. It's worth noting that the smaller the voxels, the more there will be in a scene, and that means also the block tree will become deeper, and so this has performance implications because the more voxels we have in a scene and the deeper we have to traverse the tree for each color sample negatively impacts the actual amount of memory latency and amount of memory in data that has to be transferred in order to do so. The thread manager, as you saw here, is mostly stats for the current workload it is performing, which is fairly straightforward when you watch it in action. Beyond the Nigiri manager, we have the main directional light, which had added to it a Nigiri volumetric light script. We also need a Nigiri light enabler on all the active lights in our scene as well, which should also be added, but if it is missing, add it yourself. This is so Nigiri can pick up scene lighting and use it to basically inform it that that particular light will be included in the lighting calculations. Now, if we find the camera, the rendering path has to be set to deferred, and HDR has to be enabled. Both of these are obligatory, as HDR values are what inform emissive lighting that provides the free lighting for your scene, and it uses the deferred render path because it makes extensive uses of deferred render buffers. Don't know what that is, so we will remove that. Now, if we move on to our Nigiri settings, this automatically adjusts the subsampling ratio for the GI to try and target close to 60 FPS, which it has utility for potato users, though this feature is still in development and causes some aberrations on its own. If you just care about quality, then the first thing you want to do is turn this off. This is the subsampling ratio, so at 2 it will render at 50% of the full render resolution, which provides a nice performance boost, though if you have a high-end GPU you can possibly crank it up to 1. Shadow resolution. These debug modes are basically debug modes. Oops. Should have resource usage, our tree built. Looks like our tree is built. So this will automatically regenerate the SVO, though it's generally only useful while debugging. Sunlight should be set to your main scene light. These will automatically match, these checkboxes will cause these values to automatically match the lighting setting. The lighting values set in your environment settings under the lighting panel, so that it'll automatically match your scene light, such as if it was adjusting or moving. Let's have a bit. 1 to 5. We will toggle this off and on, which will give us a little lighting. We have the temporal blend settings, which applies a mild blur to the GI pixels. GI settings probably require a video of their own, as there's a lot going on here. The major point here is race step affects performance, and the number of cones, where you can change cone settings, also have a major effect in performance. Under optimization settings, we have the depth stop optimization, which basically early exits the SVO traversal when you hit your target, rather than basically proceeding to max depth, And second pixel checkerboard basically causes it to only render alternating pixels during each frame and then temporarily accumulates them, which also improves performance. And this is cumulative to the subsampling ratio, such as if it's rendering 50% and the second pixel is set to a factor of 3, you're only rendering tracing 33% of your pixels for GI each frame. Reflection settings add basically reflections to this, basically responsible for tracing your reflections. Again, cone settings affect performance. The trace step value affects performance, as does the grid rendering, which defaults to 3 with optimized reflections on. Notice there are two options here, aggressive temporal trace and aggressive temporal trace. This basically creates a drastically reduced number of traces per frame, which helps performance by only refreshing a pixel if it's actually needed, as opposed to just basically continually redrawing the scene a few pixels every frame, which in very low performance situations can be useful. Now there's SMA built in, though this isn't to replace your actual scene anti-aliasing, which you will also need after the fact, but because it pulls the color lit values from the deferred render buffers rather than the general render output, it means it can pull in additional aliasing from the render buffers that would override the anti-aliasing you have here, and so this aids in that. So even though this is on by default, you still need your own anti-aliasing adding to the scene. In addition, volumetric lighting is based on Simply Mad's volumetrics and basically works the same way. Add GI to effect actually adds voxel colors the volumetrics with the voxel color it's passing through, which can add an artistic tint even though it's not physically accurate. It can have an artistic value, such as just regular diffuse and with the voxel colors added. Tone mapping is provided, which has basically support for either filmic or ASIS with curves. And down to the bottom, debug functions. Resource usage is how much video memory the system is using in total. Like with default settings, this is about 850 mega VRAM for the whole system to run. And from the pool it allocates both the tree nodes, which correspond to the sparse voxel tree data structure itself, and brick nodes, which are linked from the SVO, contain the actual color samples and the bulk of the data. For example, here we can see with this complete scene, it's using 1.8% of the 128 meg to the tree, and about 4.7% of the color samples. There are debug options such as 3D textures and screenshots, which you won't need. They're mainly there as a developer of the system itself, so we can actually I can verify what's going on when things go weird. Blur should be self-explanatory. Apparently doesn't want to adjust. And that's it, really, the main points. If you were to set all this up manually, you'd have to add them, manage it yourself, make sure everything's static, and add these add the volumetric to your directional light and the light enabler to every other point or every other active light in your scene yourself. And then after that, you'd add the camera, and then you'd add the mesh encoder objects. Now, I'm going to take a look at the mesh encoder objects now. So you can see there are a number of settings here. Because that's static, that should have set itself to static automatically. Basically, the default setup is fine, because if the mesh is static, this needs to also understand it's dealing with static data. as it needs to be handled differently. If you had a non-static real-time object in the scene, then you can add this, and there's two update modes. Low cost performs the recalculation on the CPU, it's light on the GPU, and only recalculates when it detects the object's transform has changed. Whereas expensive real-time re-encodes the object every frame on the GPU. It's more expensive on the GPU, but provides smooth instant updates for real-time objects. Say a player was carrying a torch or a car with emissive headlights was driving down a street. That would mean it would update in real time, which is why this is a hybrid platform, because there's support for both baked with streaming from disk at runtime and both real-time global illumination to meet the needs of the complex project built in. The sample importance box basically means that if a particular source of illumination or color is more important and it was being overpowered by, say, a wall or something next to it, then the sample importance box would give that mesh priority in the global illumination, which is a form of fine-tuning. Debug options for drawing the grids and volumes. And this here is how many voxels have actually been stored. As you can see here, the system hasn't baked everything, and so to fix that, because if that happens because you've been fiddling around and doing everything in the wrong order, you can just exit and save your scene, and it will actually detect this when you open the scene back up again and sort it out and finish baking the remaining objects. So if you actually have any problems with the behavior, you can just exit the scene in the editor, reopen it, and it will basically re-sanity check it and perform any required rebuilding for you automatically, as it will process through all your objects. So because it's a complex scene and things can go wrong, there are fail-safes built in to try and handle as many potential problems for you. Because this is going to take a minute again, I will just pause the video. Okay then, we're back in action. You normally wouldn't have to deal with that. The reason why it became a little unsynced for me was because I began baking and then fiddled around with it and flipped some static toggles which I had forgotten about, and that really is my fault. But when you first load a scene up that even has been baked, it is still going to go through and check everything in turn as it builds the dataset in edit mode. So it catches its own mistakes basically. Now then, the reason I chose this scene was not because it looks best with global illumination, but because it has about 10,000 prefabs, all needing to manage their own data. It provides a good stress test of the central thread management part of the system. We can, of course, brighten it up a bit by turning up the sunlight injection, which is an alternative for the ambient we turn down here. Now, some objects might not encode correctly or might produce weird results if they are using shaders, certain shaders, such as the here a bit while it's being all busy. Normally runs much smoother, but I am also recording and running NVIDIA broadcast all on the same GPU at the same time, and wait for that to do its thing. For example, we have this using a different shader. We just select that. set that to standard. And we will drop the normal back in. And smoothness back in. Because what happens is the color sampling and reflection calculations respect the material properties of the shader themselves. So if a shader selected doesn't actually provide a smoothness setting or a metallic setting, then unfortunately it basically defaults to the default, and that may not be what you want and produce suboptimal results. So whichever shader you want, as long as it has something called smoothness and metallic and the normals and things all built in, then it's normally good to go. Oops, just pop that out there. We're doing well at this today. Should we see what it's doing? Okay, so it's finished processing. You'll just drop that back in there. Zoom out, and okay, you're quite finished. We have our scene set up and working in Nigiri, and at this point you can begin fine-tuning. So if we were to hit play or build, the system does support builds with IL2 CPP, which are recommended as it does really make the most of your CPU cores available. And we'll see in runtime it building the lighting for the over the first few settings, as it is streaming the pre-calculated voxels from disk into memory and building the sparse voxel octree as it goes. The frame rate is suffering more than it should because my recording is competing for GPU time, but otherwise it runs smooth enough. And otherwise, that concludes this first quick start with Nigiri guide. I wish you well, and any problems, please get in touch, and I will use this as feedback for future videos.